It's a great honor to have Gilles Brassard present that. I guess Gilles is the founding father, or one of the founding fathers of the BB84 protocol, the quantum key distribution protocol that actually is commercially available these days. Nicolas Gisin is selling it, but he left, so if you want to buy it, you have to send him an email, or actually I can give you a nice price too. He also is the co-inventor of quantum teleportation, and maybe also quite interesting, he's a computer scientist who worked on cryptography for his doctoral thesis. And he's well known, he has many prizes and awards. Let me mention a few. He has the Heisenberg Canada Gold Medal. Together with Charlie Bennett, he recently won the Wolf Prize for Physics. And this is probably the second after the Nobel Prize most prestigious prize. And it's also an indicator for getting the Nobel Prize. So actually I'm hoping that you will get one soon. And so without further ado, I will give the floor to Gilles, who will talk about could Einstein have been right after all? Is Renato still here? Yes, Renato is still here, so we can at least get some opposition with respect to the view of Gilles. Gilles, please. I'm very happy that you can give this talk.
Thank you, Harry. All right. So, could Einstein have been right after all? I checked that just before. It worked. That doesn't anymore. Sorry. What? Well, just to not have this bad surprise, I checked that it worked as I was walking in. Sorry about that. I might have a talk. It unplugged. And it takes about 5 minutes to warm up. That's why I plugged it in ahead of time. Okay, so am I talking 5 minutes? Sorry, seriously. Let's start. All right, so could Einstein have been right after all? Right about what? Of course, he's been right about many things that nobody dismisses or contradicts, like gravitational waves, was recently demonstrated. And of course, that's not what I'm talking about. So Einstein, I don't need to tell you who he is, nor that he got a Nobel Prize. What maybe some of you don't yet know is that he did not get a Nobel Prize for relativity, but for quantum theory. The photoelectric effect is what he got the Nobel Prize for, and that's really a very key paper in quantum theory. And my favorite quote of Einstein is this one. And we'll come back to that at the end of my talk. Now, journalists they're very happy when they can quote Einstein because it sells well, and even more happy when they can tell that he was wrong. This particular article was in the New York Times in October 2015. And we'll come back to what it was about in a few minutes, for those who don't know yet. But just to attract your attention, this was in the New York Times, and 2015 is 80 years after what this article is actually about. In 1935, again in the New York Times, there was this press release, Einstein attacks quantum theory. I was at the Stedelijk Museum a few days ago, and I saw that quote appear on a screen about a somewhat strange exhibition. But I was not quick enough to take a picture at the Stedelijk. Nevertheless, so Einstein attacks quantum theory. Maybe this is going to work soon now. Sorry. It stopped blinking. Oh, okay. I don't know which button worked. This is a wonderful random generator. Every time I plug it in, the button that I use to go forward and backward change places. I have never figured it out. Most of the time, actually, it's the reverse button to go forward, but not always. Anyways, again, let's do it again. Okay. All right. So again, in New York Times, in May of 1935, there was this claim that Einstein attacks quantum theory. And it said that Einstein and, well, scientists, of course Einstein, and two colleagues, the two colleagues being Podolsky and Rosen. So Einstein and two colleagues find it being quantum theory, not complete even though correct. Now, when Einstein saw that in the New York Times, he was extremely angry. And he wrote back. He wrote back to the New York Times. That's a statement by Einstein that the New York Times published a few days later, 3 days later actually. It was May 4th before. So after a few days, Einstein bounced and said that he was extremely angry. Any information upon which the article is in your issue of May 6th is based was given to you without my authority. And the most beautiful part of this quote is Einstein saying, I deprecate advanced publication of such announcement in regard to such matters in the secular press. So the New York Times is the secular press. That's as opposed to Physical Review, which is a holy press. I find that really amazing. And, well, it was leaked actually by Podolsky. So Einstein was really not happy about that. Nevertheless, it is true that a few, I think 10 days later, in Physical Review, the Einstein-Podolsky-Rosen 1935 paper came out, in which Einstein and two colleagues attacked quantum theory. Yeah. So what was it about? It was about so they find quantum theory is not complete, even though correct. In particular, what it was really about is to do with the Heisenberg uncertainty principle. So let me remind you very quickly, or tell you, that Heisenberg claimed that it's impossible to simultaneously know the position and momentum of a particle. And Einstein was not happy about that initially. He kept finding counter-arguments that didn't work. So at the end, he relented. All right, it's not possible to know both simultaneously. But why is that? And most people would say that it's because measuring one will disturb the other. If you want to measure the position of an electron, you have to shine light on it, and the photon that will hit the electron will disturb it, and just the act of measuring one of the two properties would disturb the other. But that's not what quantum theory says. Quantum theory says something much more interesting, which is that the reason why you cannot know both simultaneously is because they don't exist simultaneously. An electron cannot have simultaneously a well-defined position and momentum. And that's something that Einstein never accepted. And his 1935 paper was mostly about disproving that, about proving, you must put quotes around here, about proving that in some cases at least, an electron can have simultaneously a well-defined position and momentum. Even though you might not be able to know them both, they are both there simultaneously. So that's the EPR paper, in which the very, very beginning of the abstract we have that in a complete theory, I must read this. This is very crucial. In a complete theory, there's an element corresponding to each element of reality. This is slightly cryptic, but most people will agree what it means is that everything that really is there in reality, whatever that means, if that reality is to be described by a mathematical theory, then there must be something in the theory for each element of reality in what the theory is supposed to describe or to explain. And in particular, if as this article purports to prove, if an electron at least sometimes can have both a position and a momentum well defined, and if the theory does not allow to describe both of them simultaneously, then the theory is not complete, because there is an element of reality, namely position and momentum of the particle. There's an element of reality that is not reflected in the theory itself, and therefore it's not complete. So that's what Einstein meant that by quantum theory is not complete. But this notion here that you should have this notion of elements of reality, that whatever is out there in the real world is described as a precise description, a precise state. That's what we would call realism. It's a philosophical standpoint according to which there is a real world. And that real world is in some state, and that state describes everything that can be observed. And I'll come back to what I mean by what is meant by realism in a moment. By the way, this 1935 paper by Einstein is his most cited paper. In 1905, he had his famous annus mirabilis, where he invented relativity, quantum mechanics, and proved the existence of atoms, and also that E equals mc squared, all that in the same year. But as you can see here with the recent Google Scholar search, these 1905 papers are very good, of course, but this is the one that proved the existence of atoms by explaining the Brownian motion. This is the photoelectric effect that gave him the Nobel Prize, and that's special relativity. Got some number of citations, but E equals mc squared, it's way behind the other 1905 paper. But EPR has much more cited. So here is essentially what was the EPR argument. Or what did it claim? That quantum theory, if quantum theory is correct in its prediction, meaning in what we can observe, and if there's no spooky action at distance, meaning if any action I can do at some place in the universe, I do something here, if it cannot have any instantaneous effect or fast and light effect on a remote point, which will be called no spooky action at distance, then if quantum theory is correct and there's no spooky action, then quantum theory is incomplete. That was the EPR argument. Sorry about that. When Niels Bohr read this, he was disturbed. It felt like as he described himself later, like a thunderbolt from the sky. He stopped everything to try to find an answer to that because, of course, Bohr wanted quantum theory to be complete. So he wrote an answer. His answer, somewhat strangely, has exactly the same title as Einstein's original paper. So this is the EPR paper. Don't blink. This is Bohr's paper. don't think I've ever seen that anywhere else. But Bohr, in his answer in the same year, 1935 as well, so this really was the culmination of the Einstein-Bohr debate. Most physicists sided with Bohr, saying that, all right, Bohr found a resolution. Einstein is just an old man who's just trying to cause trouble, but Bohr got it. Bohr, yeah, he won the debate. I'm not a physicist, but when I read both papers, I find both Bohr's answer pathetic. Sorry to say that. I admire Bohr, but his answer to the EPR paper is completely off the mark. He writes things that are maybe correct, but have no connection with what EPR was discussing, in my opinion. In any case, he nevertheless won the battle in public opinion of physicists, and it stayed like this for quite a while. The main purpose of this talk is to argue that, in fact, Einstein was right in this debate. Okay, let's come back to this New York Times clipping. Einstein. This was about this experiment, which took place here. By here, I don't mean Amsterdam, I mean the Netherlands. It was in Delft, where for the first time there was an experiment that was performed that claimed to be a loophole-free test of Bell inequalities, and as such demonstrates, back to the New York Times, proved that objects separated by great distances can instantaneously affect each other's behavior. In other words, spooky action. I do something here, and it has an instantaneous effect there. I'm not saying that this is what the Delft team claimed they did, but that's what journalists understood. And you got this headline everywhere, that Einstein was wrong and spooky action is real. Okay. In addition, back to again in New York Times 1935, not only did Einstein and colleagues find quantum theory not complete, but also they believed that a whole description of the physical reality can be provided eventually. In other words, that it's not complete and it could be completed. And again, he was right, because it can be completed, which is mostly what I'm going to talk about. So yes, it is possible to complete quantum theory and explain entanglement, Bell's inequalities, and all that without any need for spooky action at a distance. Nevertheless, John Bell, in 1964, John Bell proved that it's impossible for nature to be local and realistic. Realistic is what I mentioned before. I will define it more precisely later. And local means no spooky action. So local realistic essentially means that objects have states of their own, and the states describe everything that can be known about the object. And if I do something to a system here, it has no effect on the state of the system over there. So it's realistic because systems have states, and it's local, and action here has no effect there. And most people would say that John Bell proved in 1964 that it's not possible for nature to be local realistic, at least not if it obeys the predictions of quantum theory. And therefore it seems that Einstein was wrong, because it's exactly what Einstein wanted to do. Well, no, he wasn't. Okay. Let me now give you a better idea of what I mean by local, realistic, and signaling. So a theory of physics can be non-signaling, I'll tell you what it means in a minute, and everybody will agree that quantum theory is non-signaling. A theory can be local, which again I will define in a little moment. And many physicists believe that quantum theory is non-signaling, yes, but it's not local. It can be realistic. Again, I'll come back to that in a moment. But let me first explain what I mean by non-signaling and local with pictures, not with equations. I have equations in the real paper, but I want to be more fun and just give you an idea with illustrations. It's really a metaphor of what I mean by signaling, non-signaling, local, non-local. And let's start with non-signaling. All right, so here are Alice and Bob. Alice and Bob would be in a signaling universe, not a no signaling. Here is signaling, and no signaling is the non-signaling. So let me explain what signaling. Let me first explain what signaling means, and no signaling is the opposite. So a signaling theory is one in which Alice could have a magical box. It has a knob. It can be turned either to banana or to rabbit. And Bob is arbitrarily far away. And if Alice turns to banana, then instantaneously, for the purpose of the talk, I did not make it instantaneous because I wanted to speak between things. But in the signaling theory, it's instantaneously when Alice turns to banana that at Bob's appears a book on bananas. This book called Banana World by Jeff Boob, the subtitle is Quantum Theory or Quantum Mechanics for Primates. It's sort of weird, but it's a good book. It is a good book. It's a popular science book on quantum theory by Jeff Boob. Anyway, but the point here is that when Alice turns the knob to banana, something appears at Bob's. But of course, instead, she could have turned the knob all the way the other way instead to rabbit, and then a book about rabbits would appear. In this case, Schrödinger's Rabbits. Schrödinger's Rabbits is another popular science book, in this case by Colin Bruce. But the point here is that this is instantaneous. So forget about which books appear. The point is that Alice does something or something else, and something different appears at Bob's, and therefore Bob can tell what Alice has done. This allows Alice to signal to Bob instantaneously 0 or 1. That's what a signaling theory is. A non-signaling theory is the opposite, but the opposite can be subtle. So my favorite non-signaling theory is one in which we have the same setting, but Alice's device is slightly defective. When Alice turns the knob to banana, a ghost appears at Bob's, but Bob cannot see ghosts. And if Alice turns to rabbit instead, the same ghost appears but upside down, which Bob still cannot see. So because Bob cannot see ghosts or cannot tell if it's upside down or right side up, Alice does something. It has an effect at Bob. So this theory is not local. Alice does something, and instantaneously something happens at Bob. But Bob cannot see it. Therefore, it is still non-signaling. Right? So non-signaling means that no matter what Alice does, there's nothing that Bob can notice, even though something can happen, as long as Bob cannot notice it. All right, so this system looks very spooky. So Bob cannot tell. The point is Bob cannot tell what Alice has done, or even if Alice has done something or not. That's why it's non-signaling. Alice cannot signal to Bob. So this looks very spooky, but actually that's exactly the way quantum theory is. In quantum theory, if Alice and Bob share, we're going to change the box for rectilinear and diagonal measurements, instead of rabbits and bananas. If Alice and Bob share a Bell state, like a psi minus, specifically 1 over root 2, 0, 1, minus 1, 0, if Alice and Bob share this state, and if Alice, well, this state can also be written as equals proposition of horizontal vertical and vertical horizontal. And if Alice measures this state rectilinearly, then she gets at random either vertical or horizontal, and Bob gets the opposite. So that Alice, by making a measurement, by choosing to make a rectilinear measurement on her half singlet, makes a rectilinear photon appear at Bob's. A photon was there, but now it's rectilinear polarized. Whereas instead, she could have chosen, oops, sorry, wrong button. Now the same state can also be written like this, algebraically the same, so that if instead Alice makes a diagonal measurement, then she makes a diagonal photon appears at Bob. So now Alice does something which has an effect at Bob's, but instantaneously, but that effect is not. But the point is that quantum theory tells us that these two states, a random mixture of horizontal vertical or random mixture of the two diagonals, they're indistinguishable, so that in fact Bob cannot tell what happened. Okay, I'm not saying that that this is really what happens, but that's the easy way, the cheap way of describing entanglement. The cheap way of describing is that Alice did something, it has an effect at Bob's, that's the spooky action in question. But it's an effect that cannot be observed by Bob, and therefore it's still non-signaling. All right, so that's non-signaling, and local means that if Alice turns a knob to banana, nothing happens at Bob's. And if she turns instead to rabbit, well, the same nothing happens at Bob. So that's local. A local theory is Alice does something and nothing at all happens. Non-signaling, Alice does something, then something can happen at Bob's as long as it's not observable. There's a big difference between non-signaling and local. And again, everybody agrees that quantum theory is non-signaling, and many physicists believe that it is non-local. All right, so this is about non-signaling, about locality. Realistic is also something important in this here. And realistic, the way I like to think of it is by resorting to Plato or Kant, and at least their terminology, maybe not their philosophy, but their terminology, in which the claim in a realistic interpretation, the claim is that there is a real world. There is a real world, and any system has a state, which we will call a noumenal state. A noumenal is a word from philosophy. So the noumenal state of a system is all there is. All there is about this system. So the noumenal state describes everything related about this system. When I say a system, I don't want to try to be precise. A system could be a particle, could be a person, could be a planet. I don't care. An object in general. So a system has a state of its own, which is called its noumenal state. And in philosophy, so there is this noumenal state. According to Kant, the noumenal world, meaning that systems would have noumenal states, it may exist, but it's unknowable through human sensation. So it's philosophy. Our point of view is that, nevertheless, it's knowable through human thought. Not through sensations, but through thought. We can apprehend the noumenal world via some metaphysical assumptions and then mathematics. And I'll get to that. So that's a noumenal state. And then there is the phenomenal state. The phenomenal state is about all that can be apprehended. And not only with our own senses, but also with arbitrary technology. Arbitrary, of course, still limited by laws of physics. So the point is that there is a world that can be apprehended, which is the phenomenal world. But this phenomenal world, in fact, is a reflection or the shadow of the real world to which we don't have access directly. It's somewhat standard philosophy. I'm not saying that all philosophers agree with that, but there's nothing heretic about this. And now the phenomenal state, if we talk about quantum theory, the phenomenal state of a system, when I say all that can be apprehended, I don't mean all that we know about it. I mean all that is knowable about it. And quantum theory is very precise about what the phenomenal state is. It's the density operator. The density matrix is precisely defined to correspond to exactly what it is that can be known about a system. It can be observed or measured. So if you know what is the density matrix of a system, you know everything that you could know about it. This is different from what you actually do know about it, because if you do a measurement, you will learn something that was in the density matrix, perhaps, yes, but you will also disturb it. So that the density matrix is all that you could potentially learn, but once you decide to learn something, you could lose the ability to learn something else that was there before. So for those who are used to these terms in quantum foundation, this is also what would be called the ontic state. But this is not the epistemic state. The epistemic state would be what you know about the system. Phenomenal and epistemic is not at all the same, whereas noumenal and ontic is essentially the same. All right. And then to define a theory, you need to see how to go from one to the other. And specifically, when in the end we do all that in terms of mathematics instead of words, in mathematics we have a function that to each noumenal state gives you the corresponding phenomenal state. This function is a morphism in a sense. It has to preserve all kinds of structure, which is very well defined once you do the math properly. And so if you want to define a realistic theory of physics, you must do that in such a way that at the phenomenal level, it corresponds to what we can observe. And at the noumenal level, it gives us some more power in a sense. But you also need to define how to go from noumenal to phenomenal. And now when you, as an experimentalist, when you do something, if you want to manipulate a system, this system has a noumenal state, which you cannot know. It's unknowable, according to Kant. But so this system has a noumenal state. You can only have access to the phenomenal level. Still, you can do an operation like some unitary. You think that you do the unitary at the phenomenal level because all you can see, but in reality, your operation is performed at a noumenal level, which is where reality is. So at the noumenal level, you do an operation which brings the noumenal state from what it was to what it is. And via this epimorphism phi, it induces an operation at a phenomenal level. And when I have more time to give a talk about this, I have many, many slides that go into detail of noumenal versus phenomenal and how these things are manipulated. But in 40 minutes, I cannot do that. Okay. Nevertheless, let me just, without giving any detail for lack of time, tell you that once you define mathematically, this is all, I realize that these are words, almost empty words. The real thing is all done in mathematics. It's very precisely and very formal. But when you do it correctly and precisely, then you can define exactly what it means to be local and what it means to be non-signaling. Essentially, non-signaling, let's say local. Local means that if you have a noumenal state of a composed system of A and B, and you do an operation on A, then the nominal state of B does not change. So, sorry, this is what locality is. Sorry, locality means that whatever you do on the nominal state of system A will not change the nominal state of system B, no matter what the state AB is together, including entangled. So that's locality. Whereas non-signaling is the same statement at the phenomenal level. If you have the phenomenal state of system AB, no matter what you do to system A, does not change the phenomenal state of system B. So the only difference in this framework, the only difference between locality and non-signaling is the same equations define both, but locality will be at a nominal level, whereas non-signaling is the same statement at the phenomenal level. And once you define all that precisely, then you can get two theorems. The first theorem is the obvious one, that any local realistic theories are non-signaling. All that this means is that if by doing something in your system, it has no effect on the system somewhere else. If it has no effect because it's local, then it has no observable effect either. And therefore it's non-signaling. So that locality implies non-signaling is obvious. But in mathematics, it's not because it's obvious that you should not prove it. Sometimes the most obvious things are the wrong ones. So there's a proof. I'm just going to show you the proof because it's very short. We won't go through it, and I did not introduce all the symbols anyways. But the point is that there is a formal proof that if you're local realistic, you have to be non-signaling. And this, in fact, is the definition of local realism, where the pi's are projectors. So and the n's are the nominal states, and the rows are the phenomenal states. Rho has density matrix. So this is the definition of being local realistic in red, and the blue part here, this equals that, is the definition of being non-signaling. So just very simple mathematical derivation proves that if you're local realistic, you have to be non-signaling. But that's not the interesting part. The interesting part, because it's obvious. The interesting part is the converse, namely that all non-signaling theories are local realistic. That's the point. That's really the whole point of this talk. Is this very broad claim that any theory of physics that's not signaling, like quantum theory, is also local realistic. And this would be shocking, actually. How could this be? After all, standard quantum theory is non-signaling, but it's not local realistic, because in standard quantum theory, as I showed with my singlet psi minus and Alice and Bob, if Alice does something, it has an effect on Bob's. So it's not local, even though that effect is not observable, because and therefore it's non-signaling. But if it has an effect, it's not local. So standard quantum theory is non-signaling, but it's not local realistic. Hence, the statement seems to be false. Now, if you believe that, let me ask you something. Is this graph planar? What graph? This graph. Is this graph planar? I hope you will say yes, because this graph is the same as this. Right? So it was a planar graph. It's not because I drew the graph with two edges crossing that it's non-planar. In the same way, it's not because I described a theory with non-local operations in a non-local way. It's not because I can describe a theory in a non-local way that the theory is non-local. It's just because I was not clever enough to do it locally. Just as before, I was not clever enough to draw my graph without having edges crossing. In fact, any theory can be made non-local. No matter what your theory is, even if it is a local theory. Let's say you have a local theory, of physics or anything you want. You have a local theory of something. Well, I can always add invisible unicorns that chatter, 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 chatter. They're at the opposite end of the galaxy, and you just keep talking instantaneously without having any effect on anything observable. So suddenly, the theory is non-local. So any theory whatsoever can be made non-local by adding useless stuff that does non-local things. So, of course, it's possible to have a theory of physics that's non-local. In the same way that almost, not every, but almost every, let's say, every non-totally trivial planar graph can be made so it looks non-planar by crossing edges on purpose. It's really the same thing. So the claim is that, this is philosophy, the claim is that if it's possible to give a local realistic interpretation for quantum theory, or in general for any theory of physics, if it's possible to give a local realistic interpretation, then that theory is local realistic. And you don't have to buy that. But what you have to buy is the theorem that it's possible to do it. And specifically, so you have this theorem. It's mathematics. It's not a matter of interpretation or philosophy. This is a theorem of mathematics. Once we lay down the definition precisely, which you could dispute, but once the definition of what it means to be local realistic, what it means to be non-signaling, is precisely defined in terms of mathematics, then it's pure math. Forget about physics. Prove theorems, and after 61 pages, you get this theorem. So to do that, of course, you need to give an appropriate definition of numinal states. So the idea is that we start with a phenomenal theory. You're handed over, by God or whatever, you're handed over a phenomenal theory which corresponds by definition to all that you can observe. So you do observations as a experimental physicist. You do observations of your universe, and all you can do is derive a phenomenal theory. There's nothing else you can do because you only have access to what you can observe. So the best you can do is derive a phenomenal theory that corresponds to what you've been observing. And once you have a phenomenal theory, now the purpose is to take it and lift it at a numinal level. In other words, try to explain it in ways that in realistic terms. And what the theorem says is that if your phenomenal theory that you have been able to derive from observations, if that phenomenal theory is non-signaling, then it's always possible to lift it at a numinal level that is realistic by definition of being numinal, but it is not only realistic but also local. And therefore, non-signaling theories can be explained in a way that's local realistic by defining the numinal states appropriately. Now there's a small caveat, which some people will not say is small, which is that for the theorem, for the proofs to work at the moment, but we might be able to fix that. But at the moment, for the proofs to go through and get this theorem, we need an additional condition, which is that the dynamics of the phenomenal theory is reversible. So if you believe in the collapse, and if you believe the collapse is not reversible, and if you believe that it's part of your phenomenal theory, it does not apply. But if you believe in unitary quantum theory, it does apply. Okay. This theorem is also true about the so-called non-local boxes. All non-local boxes are not reversible. It's a different proof. But non-local boxes, if you know what it is, if not, that's okay. But non-local boxes also can be given a local realistic interpretation. And the non-local boxes are in fact local. And the most interesting, this is a Popescu-Rorschach non-local boxes. They are in fact local. And the most interesting part of this is that it's extremely simple. It's extremely simple to give a local realistic interpretation for non-local boxes. And non-local boxes violate Bell's inequality much more than quantum theory. So this proves that a mere violation of Bell's inequality, because you've experimentally, like the Delft experiment, no matter how much you violate Bell's inequality in actual experiments, in no way can this be considered a proof that the world is non-local. Again, because non-local boxes violate Bell's inequality, and they can be explained in a purely local universe. All right. So to conclude, I said that before. So Bell said that it's impossible for nature to be local realistic. In fact, he did not say that in his famous 1964 paper. He said it much later in his last paper in career called Nouvelle Cuisine, strange title for a paper. In Nouvelle Cuisine, I'm sorry, I forgot when it was, but very last paper, Bell made the mistake of saying this. It's a mistake because it does not follow from violating Bell's inequalities, again, that nature cannot be local realistic. What the real statement in 1964, what Bell stated and proved in an impeccably correct paper. So his 1964 paper, I have no criticism. He said, proved the statement that you cannot explain quantum theory with local hidden variables. That's what he proved, and that is correct. However, that's different. Local realism and local hidden variables is not the same thing. So local hidden variables is not the only way to be local realistic. I'll take just a few more minutes. I won't get into any detail, but just a few more minutes to tell you, could there be, of course you know the answer is yes, but could there be another local realistic way other than local hidden variables? Just that requires more imagination. And again, since it's all about Einstein, really imagination was the key to do that. We need imagination to find a way to be local realistic without resorting to local hidden variables. Because we know by Bell's theorem that with local hidden variables we cannot get a description of quantum theory. So if we want to be local realistic, we have to find a different way, different than local hidden variables. And at first it seems that it's not possible. But with enough imagination we can do it. And there are two keys towards this. The first key is that, here I assume that you know about Bell's inequalities. If not, that's sorry. But when you do a Bell violation experiment, Alice and Bob, they have their entangled system. And Alice and Bob, each one in their own little corner, will do a measurement and record the answer several times. And Bob will also do the same in his corner. And both Alice and Bob, each in their own corners, what they will see is not at all surprising. You will just see random stuff. There's nothing strange about neither Alice's measurement results nor Bob's measurement results. Things become strange only when you compare them. And to compare Alice's table with Bob's table, to compare the two sets of results, you have to bring them together. But bringing them together cannot be done faster than light. That's the key. So that the point is that Bell's inequalities are violated not when Alice or when Bob do their measurements. They are violated when they are compared. And that comparison cannot go faster than light. So you can get around Bell's theorem in that way. Now, of course, this sounds totally crazy. It sounds totally crazy because, after all, if the violation is observed at some point, well, it was already there before the data moved. So for this to make sense, you also need a second key, which is that measurement outcomes never have to become fixed and definite. So that if indeed, when Alice and Bob do their measurements, an outcome comes out and that's finished, that's fixed and definite, then they won't change when they move to be together and the first key will not apply. So you need to also realize that measurement results, in fact, that all possible results occur at the same time. So now we're on the slope to many world, although it's not many world, it's somewhat different, but it's on the same, there are strong similarities. But in other words, for the first key to give hold to anything, we also need that in fact all possible results occur simultaneously. So that there is a splitting, but not of the universe, it's a local splitting, which we call parallel lives. So Alice and Bob will locally split when you do a measurement. There will be two Alices that have seen the two possible outcomes, and two Bobs that have seen two possible outcomes. And neither Alice will see the other Alice, nor neither Bob will see the other Bob. And when they get together, it's at the moment that they get together, the handshake will be made to get the right correlations. And you need to do the mathematics to get it right, but this has been worked out. So that it's only when they meet that one Alice will see one Bob, the other Alice will see the other Bob, and everything will be fine. All right. But there's no splitting of the universe. It's really purely local splitting. All right. If you want to know more, it's all here. We won't go through that, but I just wanted to show that I said 61 pages when we do all the detail, but all the important steps are there. And you can find it on the archive. Okay. It's not a new idea, actually. Everett, who introduced many world interpretation back in 55, had most of the ideas, but he didn't care about non-locality. He cared about a measurement problem. But we need a notion of parallel universes somehow. Deutsch and Hayden worked out a local realistic interpretation of quantum theory on that last century. So it's not new at all. We did it in a somewhat different way, but and also in this book about rabbits, there's a nice, somewhat very similar is there. I think we made it simpler, but also the most important thing is that we proved, we also proved that the universal wave function cannot be a complete description of the universe, which is what most Everettians believe. If you want a local world, then you cannot take the wave function of the universe as its complete description. It's incompatible with locality. And we did what I said. We generalized to any reversible dynamics non-signaling theory can be made local realistic, including quantum theory, but any other theory that you might imagine. If it's non-signaling, it can be made local realistic. All right. I guess I should stop here. Thank you.
Thank you, Gilles. Actually, to stay within the theme of nouvelle cuisine, here I have a real box of phenomenal chocolates.
Oh.
But before that, we have some questions, maybe.
Yes?
Yes. Bunch of questions. Arnoud.
So I guess there must be unicorns in quantum theory, because it's now a non-local theory. You say it should be local and realistic. So there should be some superfluous unicorns talking to each other in quantum theory as it is now.
No, I didn't say that. I did not say that. I did not say that in order to be non-local, you have to be non-local on purpose, frivolously. But what I'm saying is that the standard quantum theory is described in a non-local way. Maybe not that doing something here will have an effect there, but that at least some randomness will appear in non-local places. And so that's a form of non-locality, which is nothing to do with unicorn speaking. My thing about unicorn was just to say that since any theory, any local theory can be made non-local, it's not because you have a non-local interpretation that you should believe it, or that you should give. A theory should be called local as soon as there is a local explanation.
So is there something in quantum mechanics as it is now that gives the appearance of non-locality? What element of quantum mechanics give the appearance of non-locality?
Well, there's this appearance. I had this diagram. This one here. In standard quantum theory, we really have the appearance of this. Whether we want to explain it, to see that this is really what's going on or not, there's appearance that if a singlet is shared between Alice and Bob, and if Alice does a rectilinear measurement, then a photon that previously was unpolarized, it was at Bob's already but unpolarized, that as soon as Alice makes the rectilinear measurement, then the photon becomes randomly polarized horizontal or vertical. This is an instantaneous effect that seems to occur at Bob's, and that's very non-local. Or else, if Alice had made a diagonal measurement, then a diagonal polarized photon appears at Bob. So this is you can explain quantum theory by saying that this is what happens. Or you can say that in a shut up and calculate version, you can pretend that you believe that, and then you calculate and everything is fine, even though you know that's not what happens. But in any case, this has a strong flavor of non-locality. So entanglement and all the Bell's experiments, Bell's inequalities, lead us to believe in non-locality, to believe that some randomness appears in remote places, but this randomness is correlated. Although it was not there before, it spontaneously appears in remote locations in ways that are correlated. You cannot. This is an non-local effect, and many physicists who would not believe that there is spooky action, like Nicolas Gisin, would still believe that spontaneously correlated randomness will appear in remote places. That's a non-local effect.
Last question.
And the point is that you can get the same predictions without believing in anything non-local.
I guess we're running a little bit late, so maybe questions deferred to the drinks. Thank you very much for
Thank you.
intriguing talk.